Okay, in the last lectures we have seen all the concepts of entropy in terms of reversible and irreversible processes. Okay, now we are going to read about entropy principle. Okay, now for understanding entropy principle we need some recapitulation of last class. Okay, so in the last class we have seen that dq by t term, when it was for reversible process, this was considered as a change of entropy. Okay, we have seen that there are number of between two points. If there are number of reversible processes, then this term for every reversible processes were same, and this term was seen that this was not dependent on the path, this was dependent only on the endpoints. That's why we have concluded that this term is going to be a property, and change of that term is known as change in entropy. Okay, so this has become a property. This has become a property which is known as entropy. But between the same points, if there are a number of irreversible processes, then we have seen that these irreversible processes, this term dq by t term for all these reversible processes are not same, and this term for irreversible processes, which we have found out that these terms are always less than the dq by t terms for reversible processes. Okay, these two things we have derived in our last class. That means dq by t term for all the reversible processes are never going to be same and are going to be always less than the dq by t term for reversible processes. Okay, now we are going to see the entropy principle. Now if we know these two things, we can easily say that ds must be always greater than or equal to dq by t. Okay, we can say that because ds is going to be dq by t reversible and always greater than dq by t irreversible. Okay, this thing we know. Okay, now if we consider an isolated system. Now what is an isolated system? Isolated system is a system in which neither mass transfer takes place, neither energy transfer takes place. Okay, so such type of systems are known as isolated system. So suppose for an isolated system, what will happen? For isolated system, this thing is going to be 0. For isolated system, this thing is going to be 0. So we can say that for isolated system, or change of entropy in an isolated system, must be always greater than or equal to 0. Because change in entropy formula is this. Now since we have considered isolated, that means no energy transfer will take place, that means no heat transfer can take place. That's why we are saying that this term is going to be 0. Now if this term is going to be 0, that means for isolated system ds is greater than or equal to 0. So same thing we have written here. ds isolated is always going to be 0. Okay, now the best example for an isolated system is nothing but an universe, because every heat transfer or anything, any energy transfer, any mass transfer, whatever that is happening, this is only interacting between the system and the surrounding, and both of these completely combine to become a universe. Okay, if this is a system and mass transfer is going to take place, heat transfer is going to take place, this is going to be there, this transfer is going to be there with the surrounding only. Okay, only with the surrounding, but this is the complete universe. Okay, whatever interaction that is taking place is going to be inside the universe only. So outside universe there is nothing. Okay, so universe is considered as an isolated system. Okay, so universe is the best example of isolated system. So we can say that del S universe is always going to be 0 or greater than 0. Okay, so we can say that del S of universe is always going to be greater than 0 because isolated system example is del universe. Universe. Okay, isolated system example is universe. Best example of isolated system is universe. So from this we can write that the entropy change in an universe must be greater than or equal to 0. Always it is going to be greater than or equal to 0 for universe. Entropy change for an universe. Okay. Now if this is the case, now universe consists of system and surrounding. Okay, universe consists of system and surrounding. Now if we take this one as greater than or equal to 0, so universe we can write that del S of surrounding plus del S of system together are always going to be greater than or equal to 0 because universe is consisting of system plus surrounding. Universe consists of, so we have broken down this universe into system and surrounding, and we have said that the change in entropy in surrounding plus the change of entropy in a system is always going to be greater than 0. In the previous class we have seen that entropy for an irreversible or reversible process, we have seen all the cases where we have found out that entropy can increase, can decrease, and can be isentropic. That means entropy may remain constant. Okay, this thing we have found out for in the last class. So all of them we have found out for either surrounding or system. Either surrounding or system we have found out. But in this class we are introducing universe, combined entropy change of both of them. Okay, so from this discussion now we can easily say that combining the discussions of last class and today's discussion, we can say that entropy of a system, according to yesterday's explanation or according to last lecture's explanation, we have seen that entropy of a system may increase, may decrease, or may remain constant. Entropy of a surrounding may increase, may decrease, or may be constant. But if we take them together, then this combined change of entropy of system and surrounding is always greater than or equal to 0. That means what? The combined, if you take a system, if you take its surrounding and you take the universe, we can easily say that entropy change of an universe is never going to decrease. From this explanation we can easily say that entropy of an universe is never going to decrease. Okay, because we have found out it from here. So in any interaction, in any system and surrounding are there, the combined change of the entropy is never going to be less than 0, whether it is minus or whether it is plus. So suppose this one is plus, okay, change in entropy is positive, okay, and this is going to be minus 2. Okay, so the final thing would be greater than 0. Okay, it can never happen that this one is 1 and this one is minus 2 and the result is negative. This thing is not possible. If this thing is 5 and this is going to be greater than 3, this is fine. This, according to our derivation of what we have found out, we can easily say that, but we can never say that. We can never say this can happen, because we have just found out that entropy of an universe is never going to change. So this thing is never going to be there. Okay, so this principle is known as the principle of increase of entropy. Okay, so this is what we are talking about, entropy principle. Okay, so the final statement is entropy of an universe is never going to be, entropy change of an universe is never going to be less than 0. Okay, the entropy change combinedly of system and surrounding must be always greater than or equal to 0, depending upon the reversible or irreversible cases. Okay. Okay, so this equation, okay, del S universe greater than equal to 0, or del S system plus del S surrounding greater than is equal to 0, this thing is known as second law of thermodynamics for a process. If you remember, in the first law also we have found out the first law of thermodynamics for a process and first law of thermodynamics for a cycle. This thing is second law of thermodynamics for a process. What was the second law of thermodynamics for cycle? The second law of thermodynamics for cycle was the cyclic integration, Closed inequality statement. That was the mathematical form, but that was for cycle. Cyclic integration of dq by t, cyclic integration, this one, cyclic integration of dq by t is always less than or equal to 0. This was the mathematical form of the second law of thermodynamics. Okay, but this was for cycle and this is for a process. Okay, now this thing is greater than equal to 0. From this is going to be equal to 0 when it is reversible process. Okay, this is going to be 0 when it is reversible process. Okay, and this thing when it is this one is going to be for when it is greater than equal to 0. This thing is going to be for irreversible process. Okay, and system plus surrounding is going to be entropy change in system plus entropy change in surrounding is going to be less than 0. It is never going to happen. So this is going to be not possible. Okay, so from the first law of thermodynamics, what we have learned? We have learned that energy of an universe is going to be constant. Okay, from the first law we have found out energy of a universe is going to be constant. And from the second law we have found out that entropy of an universe is never going to decrease. Okay, entropy may remain same, then del S plus del S surrounding is going to be 0. Okay, change in entropy, okay, for system and surrounding is going to be 0 when entropy is at least same. But when entropy change in entropy and change in entropy of system and change in entropy of surrounding is greater than 0, that means the entropy of the universe is going to increase. Okay, so these are the only two conditions. Okay, so from here we can say that from the second law we can say that entropy of an universe is never going to decrease. Okay, entropy of an universe is never going to decrease. Okay, so now we are going to see that entropy principle is nothing but a quantitative statement of second law of thermodynamics. Okay, entropy principle is the second law. That means by quantifying this equation or the entropy principle equation, that is what that entropy change in a universe is greater than or equal to 0. Okay, or the entropy change in system plus the entropy change in surrounding is always must be greater than 0. So entropy principle is just a quantification of second law of thermodynamics. To understand this, we have considered an isolated system here. How has it become isolated? Because there is no leakage in the boundary of this thing and the boundaries are completely insulated. Since it is insulated, no energy or heat transfer is going to take place, because energy transfer is not going to take place in terms of work because there is no shaft also. And since it is insulated, heat transfer also cannot take place. And since there is no leakage, no mass transfer can also take place. Okay, all the interactions will be only in between or within this boundary only. So this thing we can consider it as an isolated system or universe. Okay, now suppose this is a place with some amount of particles and this is a place with some amount of particles. Okay, so suppose this part is A and this part is B, and this part is having a temperature TA and this part is having a temperature TB. Now this place is, suppose TA is greater than TB. Okay, let us suppose TA is greater than TB. Okay, then we are transferring some heat to the TB. Okay, we are transferring heat to TB. Okay, that means what? Or suppose you can find it later. First of all, let us say that some amount of heat has been transferred from this place to this place. Okay, this place to this place. That means now we have to find out what is the entropy change for that isolated system. Now let us take the entropy change for isolated system. This is going to be isolated system. That means this is going to be del S for system and del S for surrounding. Okay, this is going to be there. Now this one is interacting with this one, so this must be the system and this must be the surrounding. Okay, so for system, what is going to be the entropy change? Entropy change is going to be dq by t. Okay, and we are considering this as reversible also. We are considering this as reversible cycle also. Okay, so now the change in heat transfer is, or the heat transfer is q. So in place of dq we can directly write q, and what is the temperature? It is giving away the heat, it is Ta. Okay, plus for surrounding, what is going to happen? Same amount of heat is coming here. Whatever heat it is releasing, this heat has been completely received by this one. So for system it is going to be q only, but at what temperature it is receiving this heat? It is receiving this heat at temperature Tb. Okay, but here will be one negative sign. Why? Because this thing is releasing this heat, or heat is going out of the body. When heat is going out of the body, that means our sign, according to our sign convention, here it will be negative. So from here we can find out that Ta minus Tb by Ta into Tb into Q is going to be the entropy change here. Okay, it is going to be the entropy change here. Okay, now we have always seen that isolated system, for isolated system the entropy change is always greater than or equal to 0. Okay, this thing we have found out. Now suppose Ta is greater than Tb. Now if Ta is greater than Tb, okay, if Ta is greater than Tb, what can happen? This value is going to be positive. Okay, this thing is going to be positive. Tb, individually Tb and Ta cannot be negative because this is the absolute temperature. Okay, so this individually they are not negative. So we can say that if Ta is greater than Tb, what can happen? This thing is going to be positive, and according to our principle, what is there? Isolated system can be greater than or equal to 0. So if Ta is greater than Tb, then this is going to be positive. That means greater than 0. If this thing can be possible, this thing can be possible. Now let us take Ta is equal to Tb. If Ta is equal to Tb, that means what? Ta and Tb are equal. That means this value is going to be 0. If this value is going to be 0, then this complete change in entropy of that isolated system is going to be 0. Okay, and if this is going to be 0, that means what? If this is going to be 0, this is satisfying our isolated system principle, okay, or the entropy principle. That means for isolated system it can be equal to 0 also. So according to the first assumption, this was entropy change was 0. According to this entropy change was greater than 0. According to the second assumption, the entropy change is equal to 0. This is also possible because we have found out that it is greater than or equal to. So for the first one we have found greater than, for the second one we have found equal to 0. But now if you take that Tb is greater than Ta, then what will happen? This thing is going to be negative. This thing is going to be negative. But according to our principle, according to our entropy principle, we have found out that for isolated system, entropy change is greater than or equal to 0. It can never decrease. Okay, entropy can never decrease. So this thing is never going to be possible. So just by the quantification of the second law of thermodynamics, the entropy principle tells us about the feasibility of a system, whether a system is going to be feasible or not. Okay, now we have cut down this assumption that Ta is greater than Tb, so that we can find out a result for this one also, these cases also. T1 is equal to Tb, then what will happen? That's why we have cancelled out this assumption. Okay, now we have seen that how the principle or entropy principle can tell us about the feasibility of a system, and accordingly we can proceed to our problems by using these concepts. Okay, so the next thing we are going to read is temperature entropy diagram. Okay, so till now whatever we have discussed, from there we are very confidently aware of the fact that the change in entropy is going to be equal to the dq by t term of a reversible process or cycle. Okay, reversible process. Okay, ds is going to be the dq by t for a reversible process. This is going to be the change in entropy is going to be the same for irreversible cycle, also an irreversible process. Okay, between the same endpoints, if we replace these endpoints or the irreversible process by a reversible process, then this value is going to give us the entropy change. Okay, in the next step what we have done, we have cross multiplied this t into ds, which is going to give you the dq. Okay, reversible heat transfer for a small portion, which is given by this. Now we are here to draw the temperature entropy diagram. Now we have drawn two mutually perpendicular axes. Okay, and the horizontal one we have named as s, and the vertical one we have named as temperature. Okay, now what happens if we draw a strip in any of the point, this is the point 1 and this is the point 2. In any of the point in between, we have drawn a small strip. Okay, parallel to the t axis. Okay, parallel to the t axis. Now, and the thickness of this is going to be ds. Thickness of this is going to be ds. Okay. Now, what is going to be the area of the small strip? The area of that small strip is going to be the height or the length of that strip is going to be t. Okay, so t into the breadth of that strip is going to be ds. So t into ds. Interestingly, this is same as this one. This is same as this one. tds, tds. Only here it is dq or here it is dn. Okay. Now to get the area of the whole area when it is projected under this curve in entropy axis or in s axis, when the area of that curve is projected, then what area you are going to get? You are going to get this complete area you are going to get. Okay, this complete area you are going to get if you project this curve on entropy axis. Okay, so what is going to be the area? This area is going to be integration of 1 to 2 t ds. Okay, this is going to be the area of the whole. This is going to be the area of the curve when projected on entropy axis. Similarly, from here, if you integrate both this, what are you going to get? If you integrate this one, you are going to get q1 to 2 reversible. Okay, q1 to 2 reversible, and this one will be 1 to 2 t ds. Okay, you are going to get t into the integration of 1 to 2 t into ds equals to q1 to 2 reversible. Okay, that means what? If you project the curve on entropy axis, then the area which you are going to get in a TS diagram, then the area which you are going to get is going to give you the reversible heat transfer. Okay, this is going to give you the reversible heat transfer. Okay, so this is the starting of our temperature entropy diagram. Now we are going to define various cycles like Carnot cycle and all in entropy diagram, which we have learned for PV diagram. Now we are going to see how these cycles are going to be in a temperature entropy diagram. Okay, but one thing we need to remember is that the area under the curve in a TS diagram on volume axis, when you project it on entropy axis in a TS diagram, then that area is going to give us the reversible heat transfer. Okay. So now we are going to represent the Carnot cycle on TS diagram. We have said that roughly in this corner, but this was not clear, so I am going to talk about it again. So this is what an ideal Carnot cycle diagram looks like in a PV diagram. Okay, this is the ideal, because if you remember, we have discussed Carnot cycle, and in this Carnot cycle we have seen that it consists of two reversible adiabatic processes and two isothermal heat addition and heat rejection. That means two isothermal processes where heat exchange is taking place. Okay, so Carnot cycle is nothing but from here to here. This is point 1, point 2. From 1 to 2, it goes from 1 to 2, so that the adiabatically the air which you are taking in Carnot cycle is going to get compressed up to here. Okay, after that some heat addition is taken place, okay, which is isothermal. Without changing the temperature, the heat addition is going to take place. Okay, now after reaching to the third point, again we are expanding that gas whichever it is in the system, okay, which is a closed system. Carnot cycle is going to happen in a closed system. So in this system 3 to 1 we are going to expand the gases. 3 to 4 we are going to expand the gases, which is again adiabatically and reversible. This process is completely reversible. Okay, this process is complete. So Carnot cycle is a completely reversible process, okay, or reversible cycle. Carnot cycle is completely reversible. So again adiabatically we are expanding this gas, and after that isothermally we are taking out the heat, and that is the reason why again the volume is coming to 0.1. Okay, so this is the representation of Carnot cycle in PV diagram. Now since we have recently learned about the temperature entropy diagram, we need to represent this Carnot cycle in TS diagram. Okay, not only Carnot cycle, whatever process we need, whatever cycles we are going to read in this chapter in next few lectures, everything we need to learn how to represent this, how to represent any cycle which is given in PV diagram can be represented in TS diagram. Okay, we need to learn how to represent a PV diagram in a TS diagram, okay, or temperature entropy diagram. So here 1 to 2 is going to be at a reversible adiabatic. Now in the last lecture what we have seen that reversible adiabatic is always isentropic. We have said a statement that all reversible adiabatic cycles are or processes are isentropic. All reversible adiabatic processes are isentropic, but it is not compulsory that any isentropic process must be reversible adiabatic. Okay, so in this process it is reversible adiabatic, which is isentropic. Okay, which is always isentropic. So in this case if entropy is going to constant, okay, in x and y line, if x is going to be constant, that means x is going to have a constant value, then it is parallel to y axis. Similarly here, if entropy is going to be constant, then it must be parallel to t axis, temperature axis. Okay, so let us draw here from 1 to 2, from 1 to 2. Okay, that means this all the points in this line is going to be getting the same value of entropy, whatever the entropy value. Suppose S1 we are taking. Okay, so all the points in this line is going to have the same entropy value, which is S1. Okay, so from again if you see from 1 to 2 we are compressing it. Now if we are compressing any gas, then the temperature of it is going to increase. Similarly you can see here that if it is T1, then the temperature is going to increase up to T2. Okay, now 2 to 3 what is happening? 2 to 3 is an isothermal process where heat addition is going to take place. Heat addition is going to take place from 2 to 3. So 2 to 3 temperature is same, and Q in is going. Q in is that means heat addition is going to be there. Again, if you remember what we have done in our last lecture, we have derived some in reversible cases. We have seen when heat is added to a system, entropy of this increases, always increases. When heat is added to the system, entropy increases. So instead of going back this way, instead of drawing the line, since we are drawing isentropic line, that means it must be parallel to entropy axis. We are going this way because entropy increases. In last class we have seen that with heat addition entropy always increases. So entropy will increase up to 3. Now again 3 to 4 it is expanding. Expanding means temperature is going to decrease. If temperature is going to decrease and it is again reversible adiabatic, so here it must be isentropic, and since isentropic it is parallel to the T-axis. Okay, it is parallel to T-axis. Again after coming to 4, that means heat rejection is going to be there. Heat rejection is going to be there means entropy is going to decrease, and again it will come up to 1. Okay, now this is Q in, this is Q in, so here this is going to be Q in, 2 to 3 is Q in, so here also 2 to 3 is going to be Q in. Okay, and this is Q out, so this is going to be Q out. Okay, now what is the amount of heat which has been added in this process? The amount of heat which has been added in this process is going to be, if you project this part on entropy axis, what is going to be there? If you project this part on entropy axis, then what is going to be there? Then the area will give you the heat interaction. This area will give you the heat interaction for process 2 to 3. Okay, so that means what? This area under 2 to 3 curve is going to give you what is the amount of heat which has been added. Since in the last board what we have seen that the area of a curve when projected in an entropy diagram in entropy axis on a TS diagram, then it gives the heat transfer. Again here heat is rejected, Q out. Okay, heat is rejected. Heat is rejected means what? What is the amount of heat is going to reject? Since 4 to 1 is Q out, here also 4 to 1 is Q out. Then if you project this curve on entropy axis, then this is the area which you are going to get. Okay, this is the amount of heat rejected. So what is the net heat transfer? Net heat transfer is Q in minus Q out. Net heat transfer is Q in minus Q out. Okay, so this is the area which will give you the complete net heat transfer. Okay, up to here. Okay, because if you subtract this small portion of area from the whole area, then this area is remaining. This area is remaining for you, which is the result of the net heat transfer. That is Q in minus Q out. Okay, again, if you want to find out the efficiency of Carnot cycle from TS diagram. Previously we have done it from the PV diagram. Okay, or empirically we have found out that efficiency equals to W out by Q in. So efficiency, what we have seen is efficiency is QR minus 1 minus QR minus Q in. Now if you take QR means what? This one. This entropy difference. Okay, so T into ds. Again, what is Q? T and entropy QR. Rejection is taking place in what temperature? Q1. Okay, rejection is taking place in Q1. Okay, so we are taking Q1. Del S is going to be same for both the cases. Okay, del S is suppose this is S3. Okay, since this is isentropic, for this process change in entropy is going to be del S equal to, here del S is going to be S3 minus S2. Okay, S3 minus S2. Here also, since both these processes are isentropic, here also del S is going to be S4 minus S1. Now S4 is equal to S3. Since this line is isentropic, S4 is equal to S3, so it is going to be S3 minus S1. Okay, again S1 is going to be S2. S1, since this line is isentropic, that means in this whole line entropy is going to be same. So S1 and S2 are going to be same. That means this del S and this del S is going to be same. So for Q rejection at what temperature this temperature is going to heat rejection is going to take place? It is at temperature T1, and Q in, that means heat addition. At what temperature heat addition is going to take place? It is going to take place at temperature 2. Okay, so T2 into del S. Del S are same for both these cases, so del S is going to get cancelled. So you can write 1 minus TL by TH. TL means what? This T1, this lower temperature, and this is higher temperature. Okay, so this is the same thing which we have derived while discussing the Carnot cycle in previous one. Okay, this is the same thing which we have derived. So this is going to be the entropy of Carnot cycle while deriving from temperature entropy diagram. Okay, we have derived in both cases. Last class also we have derived it from the empirical relation of W out by Q in, and here we are finding it from TS diagram. Okay. So till now we have done first law of thermodynamics and second law of thermodynamics. Now what we are going to do, we are going to combine these two laws of thermodynamics, that is first and second, with the help of some equations. Okay, with the help of some equations we are going to combine the first law and second law of thermodynamics. So first law, for first law, if you remember, we have seen that there are two different formulas for cycle and process. For cycle it was net heat transfer is equal to net work transfer, and this equation is for process. Okay, this is valid for reversible as well as irreversible process. This equation dq equals to du plus dw. Okay, but this equation from here we can directly write this one. Okay, but P into dV for a work we have learned it with the help of quasi-static process. Okay, so this is only valid for reversible process. Okay, this is only valid for reversible process. So these are the two things which we are getting from first law of thermodynamics. Now second law. In second law we have just found out that dq is equals to T into ds. Okay, so this is again for reversible process. Okay, only for reversible process we have seen that dq by T only for reversible process it is going to be same as entropy change. Okay, so dq is going to be equal for this one. So again if you put that TDS equals to du plus PdV, in place of dq if you write TDS, then your equation becomes TDS equals to du plus PdV. But here this is valid for all the cases, reversible as well as irreversible. Why this is valid for reversible and irreversible processes? Because both in these processes, whatever the terms you are getting, temperature, entropy, internal energy, volume, pressure, these all are properties of a system. Okay, these all are properties of a system. Now if property of a system is there and you are given certain points, then in between two it does not matter whether it is reversible or irreversible. Okay, if two definite states are there, state 1 and state 2 are there, for this point pressure, volume, temperature, entropy is going to be same value. Okay, and for this this point temperature, entropy, internal energy, volume, pressure is going to have same value. So in between them, or in between these 2 points, if there is a reversible process, if there is an irreversible process, everything you take, it is not going to matter. Okay, so since this equation is connected with all these properties, that's why it is valid for reversible as well as irreversible process. Okay, now this you can say this is the product of your combination of first law and second law of thermodynamics. But if you see we have seen that what is enthalpy. Enthalpy we have seen that H is equals to U plus PV. Okay, enthalpy we have seen as H equals to U plus PV. Okay, now if you derive this, then what will happen? dH is going to be du plus, again here it will come PV. Okay, derivation of PV term, that means what? P del V plus V del P. Okay, or PdV plus VdP. Okay, this is what you are going to get. Okay, now this one is what? du plus PdV, it is going to be your dq. This is going to be your dq. So you can directly write dq plus VdP. You can directly write dH is equals to dq plus VdP. Okay, now from here you can write dq is equals to dH minus VdP. dq is equals to dH minus VdP you can write. Now again dq is equals to TdS. Okay, so TdS is going to be dH minus VdP. Okay, this is going to be the final equation which we are going to get after combining first law and second law of thermodynamics. Okay, so this is again valid for reversible as well as irreversible processes. Again you can see enthalpy is also here. It was internal energy. Enthalpy is also a property. We have all completed this thing in second chapter itself. Okay, so this thing is again going to be equation for reversible as well as irreversible process. Okay, because as I have said, in between two endpoints, if there is some property, the property change does not depend upon the path. If the same given points or same in endpoints are given, then whatever the path it may be, reversible, irreversible, whatever the path it may be, the change in the property is going to be same for all the paths. It does not depend upon the path. So this is the result of our combination of first law and second law of thermodynamics. Okay. Okay, so now we are going to read about slopes of different processes in TS diagram. Previously we have done all the open system, closed system diagrams for PV diagram. Okay, open system and closed system, and all of them was done in PV diagram. Now slopes of different processes in TS diagram. Okay, slopes of all the processes in TS diagram we are going to find. So first of all, the process we are taking is constant temperature. So since it is TS diagram and its temperature is constant, so this must be parallel to the entropy axis. And as it is parallel to the entropy axis, the angle it is making with the S axis is going to be 0. So the slope is going to be the angle between these two, the tangent of the angle between these two. So slope is going to be tan theta. The theta is going to be 0, so slope is 0. Now reversible adiabatic process. We all know and we have found out that reversible adiabatic process is always isentropic process. And since it is isentropic, that is entropy is going to be constant. That means the entropy line is going to be parallel to the temperature axis. Okay, temperature axis. And the angle it is making, the tangent of the angle it is making with this horizontal axis is going to give us the slope. So slope will become tan theta. Here theta is 90 degree because this is vertical to this one and making an angle of 90 degree. So the slope is going to be infinite here. Okay, in the next board we are going to see the next processes. Okay. Okay, so the next processes are going to be constant volume process and constant pressure process. So first of all I am going to do for constant volume process. Since it is constant volume process, whether it will be straight line or curved line or whatever the line it is going to be, we do not know. Okay, so we are randomly drawing a line. Okay, we are randomly drawing a line, and in the previous two cases what we have done, we have drawn this straight line and we have measured the angle. But since it is a curved line, in each and every point it is going to form a different tangent. So angles in different point is going to be different. Okay, so we have to generalize the case of in the form of slope. Okay, we have to generalize this case. So again, if you remember, slope is always going to be the tangent of this by this. Okay, this side by this side is always going to give us the slope, or tangent of this angle is going to give us the slope. So in general case, we know that slope is going to be equal to dt by ds. Okay, dt, this height is going to be dt if any small portion is taken, and this height is going to be ds. So dt by ds is going to give us the slope. Okay, now we know this equation, tds equals to du plus pdv. We know this equation. Again, we have read earlier that du is cv into dt. Okay, if you remember in previous chapters, if you recapitulate, then you will see that this du is going to be cv into dt. Okay, so this thing we have derived in the last board. Okay, so now it is constant volume. Since it is constant volume, then this term is going to be 0 because dv is going to be 0. So the remaining part is tds equals to cv into dt. Okay, so from here what is going to be the value of dt by ds? dt by ds is going to be t by cv. Okay, this is going to be the slope of constant volume process. Okay, Now coming to the constant pressure process. Okay, let us keep it up to here. Now constant pressure process. Similarly, the slope is going to be same dt by ds. Okay, now this is the equation which we have got in this lecture only. Tds is going to be equal to dh minus v into dp. Since it is constant pressure, dp is going to be 0, so this value is going to be 0. So from this thing, what is going to be the value of dt by ds? That is the slope. dt by ds is the slope here. So dt by ds is going to be t by in place of dh you need to write, dt still we did not get. Okay, tds you can write dh equals to what? Dh is going to be equal to cp into dt. Okay, cp into dt. From this equation, what is going to be the dt by ds? From this equation, dt by ds is going to be t by cp. Okay, this thing also we have done earlier. dh is going to be equals to cp into dt. Okay, so from this equation, we can write dt by ds. This is the slope is equal to t by cp. Okay, t by cp. So again, this is t by cp and this is t by cv. Okay, now we have read earlier that always cp is greater than cv. cp is always greater than cv, but here cv is in denominator, here cp is in denominator. Okay, so what will happen? This thing will be greater than, if this is a constant volume, then this thing will be greater than dt by ds at constant pressure. Okay, cp is greater but it is in the denominator, so that's why this value will be smaller. Okay, so what we are getting, t by cv is always greater than t by cp. Okay, that means the slope at constant volume, this is at constant pressure. Okay, this thing is at constant pressure. So slope at constant pressure is always smaller than slope at constant volume. That means in general, if you draw this slope, constant volume and constant pressure in a single diagram, in a single T into S diagram, then slope of the constant volume process is going to be higher and slope of the constant pressure process is going to be lower. So this is going to be a constant pressure line and this is going to be a constant volume line in terms of a TS diagram, okay, or temperature entropy diagram. Okay, in the next lecture we are going to see the entropy change for different processes and we are going to solve some of the questions. Okay.